Alright, y'all, so section 2.3 is called continuous functions. Okay, a function whose graph can be sketched over an interval of its domain with one continuous motion of the pencil is an example of a continuous function. What that basically means is a function is continuous if you do not have to pick up your pencil when you draw the line or the curve of the function. Okay, so continuity test. There are 3 steps to checking if a function is continuous at any point x equals c. The first step is to find that the function does have a value at x equals c. The second step is to identify if the limit of f of x as x approaches c exists. So you would have to find the left-hand limit as x approaches c from the left-hand side, and the right-hand limit as x approaches c from the right-hand side, and if both of those are the same, then the limit as f of x as x approaches c does exist, just like we did with limits in the last section. In part 3, the limit that we find in step 2 has to equal the value of the function at x equals c, which is what you find in part 1. So this is basically saying that step 2 must equal step 1. Okay, so let's look at some examples. Our first example says the function v equals f of x is shown on the right on the interval 0 to 4. Determine using the continuity test if the function is continuous. So if we just look at this graph, clearly it is not a fully continuous function, so we're going to try to figure out if it's continuous at these various points. So our first question is f of x continuous at x equals 1? So our first step is to figure out what is f of 1. Does that exist? Okay, so if we go over to 1, we have an open circle at 0 and a closed circle at 1. So f of 1 is that closed circle. So f of 1 is equal to 1. The next thing we need to do is figure out if the right-hand limit equals the left-hand limit. So we need to know what the limit as x approaches 1 from the left equals, and what the limit as x approaches 1 from the right equals. So as x approaches 1 from the left, our limit is equaling 0, and as x approaches 1 from the right, our limit is equaling 1. These do not equal each other, so our limit as x approaches 1 of f of x does not exist. Therefore, f of x is not continuous at x equaling 1. Okay, let's try to figure out if f of x is continuous at x equals 2. So again, our first step is to find what is f of 2. So at f of 2, we have an open circle at 1 and a closed circle at 2. So f of 2 equals 2. Now we need to find the left-hand limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. So from the left, as x approaches 2, our graph gets closer to 1. And from the right, as x approaches 2, our graph gets closer to 1. So our limit as x approaches 2 of f of x is equal to 1. And then our third step is to determine if our limit as x approaches 2 of f of x is equal to f of 2. So when we did our math, we found out that the limit is equal to 1 and f of 2 is equal to 2, which are not the same. So f of x is not continuous at x equals 2. Okay, so for x equals 3, I want you all to try that on your own, and we will move on to the next page. Okay, so for problem number 2, we have the function x squared minus 4 divided by x minus 2, and we want to know, is f of x continuous at x equals 2? So our first step, remember, is to figure out what is f of 2. So if we substitute 2 into this function, we have 2 squared minus 4 over 2 minus 2, which is equal to 0 over 0, which is undefined. Therefore, because f of 2 does not exist, the function is not continuous at x equals 2. Now let's look at these piecewise functions. So depending on what we're looking at, we are going to need to use various parts of the piecewise function to help us find it. Our steps for determining continuity is still going to be the same, however. So first thing we want to do for number 3, when determining if the function is continuous at x equals 3, is finding f of 3. And using our piecewise function, we know that the bottom function is the one that we use when x is equal to 3. Therefore, to find f of 3, we will substitute 3 into our bottom function, and we get 3 times 3 minus 5, which is equal to 9 minus 5, which is 4. Then we need to determine the left and right hand limits of the function. So we want the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right of f of x. So when x approaches 3 from the left, we know that all the values of x are less than 3. So we'll use our top function to figure out what is our function going to be approaching from the left side. So we'll substitute 3 into our top function. So 3 plus 1, which is equal to 4. And then in order to find what x is approaching from the right of 3, we know that our values of x are going to be greater than 3, so we'll use our bottom function once again. 3 times 3 minus 5 equals 4. And because these are the same, we know that the limit as x approaches 3 of f of x will equal 4. And then our last step is to determine if the limit as x approaches 3 of f of x is equal to f of 3. We know our limit is equal to 4, and f of 3 is equal to 4. Therefore, the symbol of 3 circles in a triangle means therefore. So therefore, f of x is continuous at x equals 3. You can use the same logic and steps to determine if f of x is continuous at x equals 1 in example number 4. And we're just going to look at example number 5, where we are looking for a value of m to make f of x continuous at x equaling 2. So in this situation, we have an initial section of our piecewise function when x is less than or equal to 2, which says that the function should be 2x squared minus 5 when x is less than or equal to 2. We also know that the function is 6x plus m when x is greater than 2. Okay, so for example number 5, our steps are still the same. Our first step is to determine what is f of 2. Luckily for us, f of 2 will occur in our first equation, where x is equal to 2. So we'll just substitute 2 into our first equation. 2 squared is 4, times 2 is 8, minus 5 is 3. Now, our second section, where we need to find the limits for the right hand and the left hand side of 2, is where things get a little bit more complicated. So, if we're looking for the left hand side of 2, we're looking for values of x where x is going to be less than 2. So we'll use our first equation once again. So substitute 2 into our first equation, and we get that will be equal to 3. Now, for when x is approaching 2 from the right, we need to use our second equation, which is 6 times 2 plus m. Now, when we simplify this, we get 12 plus m. Now, our goal is to find a value of m where f of x is to be continuous. And we know that in order to have continuity, the left hand and the right hand limits must be the same. So, if we set our left hand limit of 3 equal to our right hand limit of 12 plus m, we see that m must equal negative 9. So, when m equals negative 9, then our right hand limit becomes 12 minus 9, which is 3. Therefore, the limit as x approaches 2 of f of x would equal 3. And our third step of continuity is proving that the limit as x approaches 2 of x equals f of 2, which we did because the limit was 3 and f of 2 was also 3. Therefore, when m equals -9, f of x will be continuous at x equals 2. The next topic of our notes talks about the intermediate value theorem for continuous functions. It states that a function y equals f of x that is continuous on a closed interval a comma b takes on every value between f of a and f of b. So what that means is that if I have an interval from a to b and my function is continuous, which means that when I draw this function I am not picking up my pencil in any way, then there is some point C in between a and b where the y value will also be in between f of a and f of b. So, let's look at some examples. In pre-calculus, you use the method of synthetic division to determine zeros of a polynomial function, such as f of x equals x cubed minus x minus 1, which is graphed on the right. So what we did here was use synthetic division for two random values of x. Okay, we wanted x of 1 and x equaling 2. When we used synthetic division, we found that when x equals 1, y equals -1, and when x equaled 2, y equaled 5. Based on this information, my y values went from a negative number to a positive number. And the only way that could happen is if it passed through the value of 0. So on a continuous function, in order to go from negative to positive or positive to negative, you have to cross the x-axis. You have to cross, at some point, the value of 0. So based on these two pieces of information and the intermediate value theorem, we know that there must exist a point where y equals 0, because my y is going from negative to positive, and x equals c. And based on the intermediate value theorem, we can say that c is between 1 and 2. Because we use the values of x equaling 1 and x equaling 2 to see the change in signs for y. So, f of x is a continuous function on the closed interval 1 to 2. So by the intermediate value theorem, f of x must have every value for y between -1 and 5, including 0. Therefore, f of x equals 0 for some value of x between 1 and 2. So on to the next page, we see a table, and it states that the data in the table gives the position s of a moving body for various values of t. The position s of t is a differentiable function. We will get into differentiability more when we get into chapter 3, But just know for now that in order to be differentiable, this means that our function must be continuous. So given this table, we want to know the minimum number of times the position of the body is 40 feet. So knowing that our function is continuous means that when we graph these points, or if we graph these points, we will never have to lift our pencil. So what we're looking for are the number of times in which our table for S changes from a number less than 40 to a number greater than 40. Because we know that in that span, our graph has to cross 40 feet. So the times that happens does not happen here because both of these numbers are less than 40, still less than 40, and then here we have 36.5 and 44. So somewhere in here, S of t has to equal 40. And if we keep going, now these are greater than 40. And then back here at the end, again, we see this 44.0 and 36.5, so somewhere in here, S of t also has to equal 40. So in order to justify this, we need to prove that by the intermediate value theorem, our data will be 40 feet at least 2 times if graphed. So, since we know that S of t is differentiable, therefore S of t is continuous. And we know that S of 1.0 is equal to 36.5, and S of 1.5 is equal to 44.0. And 36.5 is less than 40, which is less than 44.0. So the position must be 40 feet at least once between t equals 1.0 and t equals 1.5. By IVT. So that's how we justify our first section between the 1 and the 1.5. But when we looked at our table, we knew that this happened more than once. So we want to also justify that this happens when S of 3.5 equals 44.0 and S of 4.0 equals 36.5. So again, 36.5 is less than 40, which is less than 44.0. So the position must be 40 feet at least once between t equals 3.5 and t equals 4.0, by IVT. So given these two statements, we can conclude, therefore, 2 is the minimum number of times the position is 40 feet. And that concludes the notes for 2.3 on continuous functions. Be sure to come in tomorrow in class with any questions that you still have regarding this topic.